Well, hello there, and happy Wednesday to all of you. This is Mrs. Sharp. Going to talk to you today about some Unit 3 stuff, but before I do that, I want to explain to you what you're looking at in front of you, hopefully, which is your Unit 3 Atomic Theory notes or guided questions. They look a little bit different this time, and on the screen, hopefully, is the same thing that is on the front of the packet you were given today. What I've done there for you is listed all of the learning targets we're going to look at this unit. So you can see that there are 8 of them. And on the front page there, I was hoping that this would help you take inventory of what those learning targets are and kind of where we are at, how we are progressing through the unit. So you can see for each one, there is the actual learning target itself, and then there's a little box or a blank to check if notes have been taken, if you did some practice problems or a lab, if there was an assessment taken, an LTA, what your score was, if you need to take a reassessment, yes or no. So to help you keep track a little bit better, see where you're at, maybe what you need to do to reassess, that kind of thing. So an organizational tool for you. You're welcome. I know you were thinking thank you, that's why I said that. All right, so these are your learning targets. You can see that we have atomic theory happening, and we're going to focus today on 3.1, which is describing Dalton's atomic theory and explaining in what ways it differs from modern atomic theory. We're going to talk about some subatomic particles, and then we're going to get into 3.2 a little bit as well. Specifically, we're going to do this part right here, which is just to describe the cathode ray tube experiment and how it helped to discover the existence of the electron in the atom. And then we're going to stop, and we'll do the rest on Friday because on Thursday we have to do some more lab stuff and finish that up. So without further ado, here we go. Starting off talking 3.1, describe Dalton's atomic theory and explain in what ways it differs from modern atomic theory. So the question says, what is Dalton's atomic theory? How is it different than modern atomic theory? And what you have there are 6 statements with some fill in the blanks, and that will help you with Dalton's atomic theory. So, here we go. There's John Dalton, good-looking guy. He's the one who's responsible for this theory. This was published in 1803 by John Dalton. And here's what he said. Number 1, elements are made of tiny particles called atoms. Nothing new there. It was at the time, but not now. Number 2, there's a little star by it. We'll see why in a second. Atoms are indivisible and indestructible. Indivisible meaning I cannot break them down into tinier pieces, and indestructible meaning I can't obliterate them off the face of the universe. Number 3, all atoms of the same element are identical. Another star next to that one. Number 4, atoms of different elements are different. So it kind of goes with number 3. Number 5, atoms of one element can combine with atoms of another element in whole number ratios to form compounds. This statement here eventually became a law, so I'm going to go ahead and write that in. You can write it next to there. You've got some room. This statement eventually became what was known as the law of multiple proportions. We had been talking about in 2.5 the law of definite proportions for a compound. This is the law of multiple proportions, and what this means is that if I have a compound like carbon monoxide, if it combines with carbon and oxygen in a different ratio, that's going to be a whole number ratio. So I'm going to have CO2, a 1:2 ratio. That ratio is going to be whole numbers. So you're never going to see like a C0.5O2. Okay, and the 6th statement there says, in chemical reactions, atoms are separated, rearranged, or combined, not made or destroyed. And this one right here was also eventually turned into a law, and that was the law of conservation of mass. or sometimes it's called the law of conservation of matter, and we've dealt with that one quite a bit. So atoms can be separated, rearranged, or combined. All right. Now the ones that are starred here are ones that were later changed. So in the modern atomic theory, we know that number 2 and number 3 are no longer valid. Atoms can be divided into smaller pieces. In fact, in the modern atomic theory, we know that they are broken into subatomic particles. Sub meaning smaller, atomic meaning atom, so smaller than an atom. Subatomic particles. And number 3 was changed because of the existence of isotopes, which we're going to talk about in much more detail in a few days. But John Dalton was kind of the first person to talk about atoms in any kind of detail and relate them to chemical reactions. The law of conservation of mass. We've talked about this, but just kind of a review. Once again, mass cannot be created or destroyed in a chemical reaction. This was work was done by Lavoisier in the 1770s. Should know this already. The mass of the reactants before equals the mass of the products afterwards. In a chemical reaction, you always start with reactants, and then you have an arrow indicating a change of some kind, and afterwards you have the products. There's Lavoisier. He was quite the ladies' man, apparently. All right, now I've got a big old table here, and we want to talk about some subatomic particles. This table matches yours exactly, and I know how you guys kind of work here, and you're going to want to just write all this down. But let's, if you don't mind, let's go through one row at a time and talk about each one of these subatomic particles. A proton, from now on, we're going to symbolize with a small p with a superscript, a high and small plus sign, because it has a +1 charge. And I think you guys are familiar with a proton having a positive charge, but I want you to know that its magnitude is 1. So it's a +1 charge. This is its actual mass, 1.673 times 10 to the negative 24th grams. But we don't really care about its actual mass because it's so ridiculously tiny. So what we're going to deal with instead when we're talking about these really super tiny particles like atoms and then subatomic particles are AMUs. And that's a relative mass. An AMU stands for atomic mass unit. And the reason it's called relative is because it's relative to another atom, and that atom is carbon-12. So one atomic mass unit is equal to 1/12 the mass of a carbon-12 atom. So that's down underneath your chart. Make sure you get this part in here, please. One AMU is an atomic mass unit. It is 1/12 the mass of a carbon-12 atom, and there should really be a dash right there. So that's your relative mass. The location of the proton is in the nucleus. Hopefully you know that already. Let's go down to the second row. A neutron, we have N superscript 0 because a neutron's charge is 0. So it's neutral in charge, but its mass is very similar to the mass of a proton. So its relative mass is exactly the same in AMU, and it is also located in the nucleus. Now, because these two things live in the nucleus, we refer to them as nucleons. Nucleons are things that live in the nucleus. Again, I really don't care if you know the exact mass of a proton or a neutron or an electron for that matter, but I am interested in you knowing the relative mass. So let's talk about the electron. Electron is E superscript negative. Its charge is -1. So one thing that I want you guys to notice is that if I have one proton and one electron, they would cancel each other out exactly. So if I have a +1 and a -1, then that would be a neutral charge. So essentially you've got, if you had one of each, you'd have +1 and a -1. Those two would be neutral overall. That's a 0. Goose egg. Look how tiny the mass is of an electron, but it does have mass, so therefore it is matter. Its relative mass is 1/1837 of an AMU, and I have 0 in parentheses because it's not 0. It can't be 0 or it would not be matter, but it's really, really close. It's essentially nothing. It has very, very tiny mass. So the mass of an atom comes from the protons and the neutrons, but the volume of an atom comes from the electron cloud, which is where the electrons are zipping around, outside of the nucleus. So electrons are not nucleons, they are zipping around in the electron cloud outside of the nucleus. So what I'd like to do now is take a second and back up and talk about some experiments that led us to discover these individual subatomic particles. Because if you remember, one thing that John Dalton said is that atoms are indivisible and indestructible, right here. So what led us in 1803, which in the relative scheme of things was not that long ago, to saying atoms are indivisible, to now knowing that they're actually made up of these protons, neutrons, and electrons. So we're going to look at some of these experiments that led us to know that. So we're going to switch to 3.2, and even though there are 2 experiments in the learning target, cathode ray tube experiment, and over here the gold foil experiment, today we're just going to focus on the cathode ray tube experiment. So the question says there on page 3, what is the cathode ray tube experiment and how did it help with the discovery of the electron? So the cathode ray tube experiment was designed to study these cathode rays inside what was called a Crooks tube. So some guys who were studying this were Crooks, that's where Crooks tube comes from, J.J. Thomson, and Millikan. And essentially what this Crooks tube is a glass tube with a very small, get this out of the way here, the very small amount of a gas inside. And that could be whatever gas you wanted it to be, like helium or neon or argon, hydrogen, as long as it is a very small amount. And then what happened, and you can see this in the picture that you have there, is that it was hooked up to an electrical current at either end so that an electrical current would go through. And what would normally happen with a Crooks tube is what you see right here. And that is this beam that would go straight across from one side to the other. That was normal. Now that's not what you have on your sheet. We're going to talk about that in a second. But normally if you had an electric current, so there'd be some kind of current source like a battery hooked up to this, and you could see this beam going straight across the tube from one side to the other. Now there is Crooks, good looking guy. There is J.J. Thomson. And there is Millikan. And if you want my opinion, I think Millikan is definitely the creepiest looking. He's staring at me right now. I don't like it. Okay, so Sir William Crooks, who the tube was actually named after, noted that this beam would show up. So I said this worked, but that the beam would show up regardless of what kind of gases he used in the tube and regardless of what kind of metal was used in the plates. And what that meant is that whatever was causing this beam to appear was in everything. So whatever was causing the beam to appear was present in all kinds of substances. So it wasn't like just special, like just neon gas caused this beam to appear. It was every gas that he could test. It was every kind of metal that he used for the plates. It was every combination that he could come up with. So whatever it was present in everything. There he is again. So what was really interesting about this is that then Crooks decided to play with this a little bit more. And this is close to what you have on your sheet, except for the plate is bending a different way, because on your sheet, the positive and negative plates here are switched. So what Crooks did, back up here, is Crooks put charged plates on the top and bottom of his cathode ray tube. So remember, normally the cathode ray would go straight across. But he found that when he put these charged plates, and again, yours is opposite, that's why it's bending up instead of down. So if you just imagine this picture upside down, you got the same thing. If you put these charged plates on the outside, then this ray would bend. And it wouldn't go straight across. They would actually bend down, and it would always bend down towards the positive and away from the negative every single time. Which led him to believe if the particles were attracted to the positive plate, it meant that those particles must have a negative charge. Up until not too long ago, when we started to have the plasma screen TVs, if you know anybody who's got a really one of those TVs with the really deep backs, that's what's in there, is a cathode ray tube. So that's why TV is sometimes called the tube. I don't know if you guys have ever heard that before. Like I'm gonna watch some tube. What's on the tube? Because there's actually a cathode ray tube in there, and the ray would strike the front of the TV and cause an image to appear. So that's where the original TVs came from. So, here's some guys again. So John Dalton, we went from saying, and I know you guys don't have a lot of space to write this right now. Let me see. You do have some on your very last page is blank, but here's kind of how the atom progressed. I really feel like you should write this down. So on your very, very last page is blank. We went from John Dalton saying that the atom was solid and indivisible, like a ball. So I think of it as like a bouncy ball. It was indivisible, indestructible. It was just one solid atom. And then J.J. Thomson and Crooks came along. And because of the cathode ray tube and the fact that it was bending, what they imagined is that it was a solid ball like this, but the electrons were kind of embedded on the outside. And that's why they were attracted towards the positive, because all these electrons were on the outside of the atom. And then the positive charge was this weak force that was kind of spread out in the pink ball part. So the electrons were kind of stuck on the outside. All around the outside were the electrons. And then the positive was spread out through the rest of it. So what they did is they had this positive solid sphere with the electrons, the subatomic particles that were negative, embedded in the surface. So they called this the plum pudding model. And they said it looked like tacks in a rubber ball. Well, the plum pudding model came from an actual food called plum pudding. So here's what they imagined, those electrons stuck in the surface. And here is an example of a holiday dessert, plum pudding. So you can kind of see the sphere and then the raisins or plums or whatever it is stuck around the outside. And that's how they envisioned it. Now obviously we know that this is not what an atom looks like. I don't think in any class you've been taught that this is what the atom looks like. So obviously the model developed from there. But based on John Dalton's theory and then the Crooks tube experiment, this is where we're at. So I'm going to stop there and just remind you that you need to do your pre-lab questions with your partner today on a separate sheet of paper, please. Or on the back of your lab, I guess, would be fine if you have room there. Some of you do. Also, you're going to be doing some practice problems or answering some questions, and those questions that you have to answer are only having to do with the cathode ray tube experiment. So any that you see about gold foil, the gold foil experiment, you can skip. We're going to do that on Friday. So I hope you have a wonderful day, and I will talk to you tomorrow. Bye.